Today we're going to take a look at an example that's slightly different than the course material shows. It's not necessarily that you have to do it this way or have to do it that way. It's just an alternative that might make more sense to you. As I have taught over the years, there's always more than one way to do the same problem, and for some students one way works a little better than the other. And for this one we're going to look at the definite integral from 0 to 2 of x times the quantity x squared minus 4 to the 5th power times the dx. Now, notation-wise, this dx, some of you kind of think that's not all that important, that it's not necessary in the integral. Well, you really haven't seen where it does become important, and through substitution and through my alternative route for using substitution on this definite integral, we will see a good use for this dx. Now, ultimately, this dx is saying our integral limits are going from x equals 0 to x equals 2. Now, we don't have to put the x equals on there. We just, because of this notation, we know it is dealing with x. So, as we run through the substitution, definitely fairly straightforward substitution. We let u be the inside here of the 5th power. I don't think algebraically we want to take that binomial to the 5th power. We could, but it would be really ugly. So then du will be 2x dx. Now, at this point, the course material kind of goes in a little different direction than I do. It will say, well, we have the x dx, so let's just solve this equation for the x dx. And we divide by 2, or multiply by 1/2, and we get x dx on the other side. So this x dx now becomes 1/2 du. So as we do the substitution, we'll end up with u to the 5th and then times 1/2 du. Well, we're kind of not doing this quite right here. The notation is not quite right. Notice we have the du, but our integral limits are still in terms of x. So we're going to need to erase those integral limits, because they're not part of the antiderivative process, and we'll take care of that. We'll reintroduce those limits once we get this done. So what we would do, we're integrating u to the 5th du and then multiplying by the 1/2, so by the power rule, u to the 6th over 6. Now, for an antiderivative, we'd put a plus c on there, but we need to go back to our definite integral from 0 to 2, and we can use our fundamental theorem of calculus. So let's see, we'd have really 1/12 with the 1/2 and then the 6 in the denominator. U to the 6th, well, u is x squared minus 4, and that would be to the 6th, and then we evaluate this from 0 to 2. So 1/12 times, plug our 2 in, 2 squared minus 4 to the 6th, and then minus, plug our 0 in, and okay, you got to be careful here. We get 0 for this part, and then minus 4 to the 6th on this one. So we'll have 1/12 times negative 4,096, and we can simplify that to negative 341 and 1/3. 341 and 1/3. Let me get that 1 in there. Yeah, 341 and 1/3. And that would be our correct answer, and this is the direction that the course material takes us. Now I'll show you a couple little differences in this technique, differences in a couple different places. One will be here, where we find dx rather than x dx, and then the other will be with the limits. Instead of changing it back to x, we'll make it in terms of u. Now the alternative to the direction we went on the first page will show up in solving. We still do the substitution, and this time we get du equals 2x dx, and we're going to solve this for dx only, and that will leave us with du over 2x. Now as we resubstitute, well, we still have the x there, the inside is u, and then dx is our du over 2x. As we simplify this expression, we notice x divided by x, those will cancel out, and we have exactly what we had the first time around, just a slightly different approach. We still have the 1/2 integrating u to the 5th du. Now notice in this case, we did not put the integral limits because we're in terms of u instead of x, and x is what's going from 0 to 2. However, let's take a look at what this would be in terms of u. This would be our second slight difference from our first time through. If x equals 0, then what is u? Well, if x equals 0, u squared minus 4, or not u squared, x squared minus 4, we would have negative 4 as our lower limit in terms of u. When x is 0, u turns out to be negative 4. Then we go to the upper limit and say, well, if x equals 2, u equals what? And x equals 2, 2 squared minus 4, u equals 0. So now we're in terms of u completely. We don't have to go back and resubstitute this in for u to integrate, to use our fundamental theorem. What we can do at this point, simply find our antiderivative, which again would be u to the 6th over 6, and then we can integrate from negative 4 up to 0. And so, as we saw the first time around, we had the 1/12, and now we plug in 0 for u, then minus, plug in negative 4 for u. And that turns out to be 1/12 times a negative 4,096, just like we saw in the first one, which will once again be negative 341 and 1/3. So we get exactly the same answer, just a slight difference in the details in how we go about finding that. By substituting everything, even the integral limits, into terms of u, we do not have to go back to x at this point, and then plug in x equals 0 to x equals 2. So again, it's whatever your personal preference is, whichever way works best for you, do it that way.